Okay, today what I'm supposedly going to talk to you about is right here, and that has to do with why fret doesn't just depend on the distance between them. You remember it goes like r naught over r to the 6th power, but also depends on their relative orientation. Okay? And the answer is really very simple, in that what you actually have in a fluorescent molecule is a transition dipole moment. And a dipole moment has a directionality to it. You know, you can think of it as a dipole, which is like a plus and a minus, so the net charge is 0, but there is physical separation between the two. And then you also know by electromagnetism that if you have these charges are accelerating, then they will tend to emit radiation. So what actually happens is you have a molecule that has this transition dipole moment, and again, and you come in with light, and the light is an electromagnetic wave. Okay, shut off. Now it's on. It's an electromagnetic wave. It interacts with the dipole, and when the plus is going like this, you know, the plus charge tends to move that way, and the minus charge tends to move that way, and it's a little bit, and then the electric field goes the other way, and the charges are basically oscillating. So what happens is it takes that oscillating field by the incoming light and then produces its own light, and that's the radiation. Now it very much depends on the orientation of the incoming light, because if you have a plus and a minus here, and you have an electric field that looks like this, that's coming in like this, it has a big effect. But what about you have a plus and a minus here, and you have an electric field like this? In general, it doesn't have a big effect. And well, okay.
Could there be multiple input sources on the projector, and this is on the wrong hand?
Yeah, that's what I did there. Just give it a minute to think about it. So the incident light, it is absorbed or not depending on the orientation, the polarization of the light. And that, at the same time, if you look at the emitted light, it will tend to be oriented with the dipoles, because the oriented light will be polarized. On the other hand, there's another effect here. There's the polarization of the incident light. But let's say instead of just being static, that the dipole moment gets absorbed by the light in a particular direction, but it then moves, and and instead of going like this, it then looks like this. Well, then the output actually will tend to be like this instead of like that. And in the case where it moves very rapidly compared to what? Good, exactly. Compared to its lifetime, it will tend to be unpolarized. And so what you want to do, so the question is why fret depends on the polarization of the light. Because you can see that there we were talking about a donor. And now you're talking about a donor and acceptor. Let's assume that you just come in and you just excite the donor. The same thing happens between the donor and the acceptor. If the donor, let's say everything's static, the donor is like this, it gets excited, it creates an electric field, and let's say the acceptor looks exactly the same as this. In which case, the transfer of the electric field will be quite intense, where if the acceptor looks like this, the transfer of that field won't be intense at all. In fact, it'll be 0. So there's a parameter generally called kappa squared that varies all the way from the donors and the acceptors being totally misaligned, in which case it's 0. So the R naught is essentially 0. You won't get energy transfer. All the way to the kappa squared being, turns out, happens to be 4. In which case, there you'll get an incredible, really impressive amount of energy transfer. Okay, so the energy depends on plus R over R naught to the 6th. Okay, this is where each time I have to go through this. If R goes to 0, this goes to 1. That's good. If R naught goes to really big, this goes to 0. Okay, so this is apparently correct.
You mean just regular R naught, right?
As opposed to the irregular R naught?
No, I mean without the subscript. You said R naught goes to infinity?
No. Oh, I'm sorry. I said R goes to infinity. Okay?
Sorry, Professor.
Yeah.
Can you just write on set?
Oh, sure. Yeah, no problem. Okay, and this time I don't have to go through my magic because I can just look right over there. Okay? And we say that this is 1, and this is 0, and where R is equal to R naught, this will be 50% or 0.5. And now we're saying that R naught must depend on this value of kappa squared. What else does it depend on? Let's say the dye has the two dyes that you're looking at, the acceptor and the donor, then what does the efficiency look like? It has to be a property of the donor and the acceptor. What does it depend? It depends on kappa squared and depends on what else? I mean, we've talked about this before. What else? Okay? You go and think about it. It'll wake your brains up a little bit. Go ahead and discuss it. Yeah, go ahead. Don't talk. Yeah.
What is kappa?
Well, lifetime.
Which kappa?
What is kappa?
It's some factor that depends on the orientation of the two gut dyes. And what we said is offhand that it's large, happens to be 4 if the two dyes are completely aligned, and it's 0 if they're completely unaligned. And we'll talk about how to determine that exactly. But so it basically depends on kappa squared. Okay. So what else does R not depend on? He says spectral overlap. Where'd you get that from? It sort of seemed like somebody had pulled it out of the hat.
I think it's spectral overlap. It's how it's the spectral overlap between the absorption emission spectra of the donor,
Yeah.
and the absorption spectra of the acceptor.
Yes, good. It's how well can the acceptor take energy from the donor, and that's true if it has absorption at the frequency that the donor. So that's generally known as J, the spectral overlap. And in fact, the J is equal to the integral of, well, the fluorescence of the donor as a function of wavelength and the absorption of the acceptor, again, as a function of wavelength. And then, if you want to know the truth, I'm always confused. I think that there's, I don't know, maybe a lambda squared or something, d lambda, integrated over all of lambda. Because, you know, this isn't emitting just at any one lambda, and this isn't absorbing at any one lambda. There's a range, basically. You know, the donor looks like this, and the acceptor absorption looks like this, and then what counts is the area in between. Yes?
So what is that J exactly?
J is what we call this. So what we call the spectral overlap. And it's the overlap between the donor's emission and the acceptor's absorption. Basically, graphically, what it says is if you plot out, here's the donor emission, and you plot out the absorption of the acceptor, that the integral, this J factor, is going to get larger the more area that they have in common. You think about it for just a minute, and then I'll come back to you. Yes?
So if we're to add terms that would contribute to R naught, there should be the distance between the donor and the acceptor?
Well, that actually doesn't have to do with R naught. That is taken up just in this value of R.
I see.
Yeah. And the R naught is a function of just the individual dyes. And if they have a lot of overlap, and if they're in the correct orientation there. And it turns out that you want, yeah.
I was just, would heat have anything to do with it?
Actually, we can turn on the lights since we've, would heat?
Yeah.
Not really, because it's the optical overlap between the donor and the acceptor. Although it's true, to the extent that when you go and excite the donor, you don't actually excite anything in terms of, imagine you went in and excited the donor, and it didn't produce an electric field at all that couldn't interact with the donor, with the acceptor. Well, then you wouldn't get hardly any energy transfer. And that's, in fact, what you have Q sub D, the quantum yield of the donor. And then it turns out you have the index of refraction of the water, or the solution that is between the donor and an acceptor, because the actual wavelength that really counts is not just the donor's emission in general, but it's the donor's emission actually in the solution. And that solution can mess with the donor a little bit. And so there is actually a donor term. I think it's actually donor to the fourth. I mean, not donor, the index of refraction to the fourth. And, okay? Okay, and what we said is the kappa squared is greater than 0 and less than 4. So if it's 0, the R naught is 0. Very small. Is this right? If R is much greater, goes to infinity, this gets very big, and that goes to 0. Okay. Okay, and if they're aligned, then the R naught is very big. And it depends on how stationary the donor and acceptor are. Because we said at first, if the donor moves a lot during its excited state lifetime, then the electric field that it produces will be at sort of all orientation. And similarly, if the acceptor varies a lot during its excited state lifetime, it'll tend to absorb at somewhere it'll be at the right position, so it'll absorb. And it turns out this kappa squared is usually a big unknown. But And what is usually taken is that it's equal to 2/3. What? Anybody have an idea for why kappa squared might be 2/3? Let's say you have a donor that's completely randomized, and you have an acceptor that's also completely randomized. That is, during their excited state lifetime, you know, it wobbles all the way around. In that case, you'll get some energy transfer. You'll never get none, and you'll never, you know, only very rarely as the thing's spinning around will they actually be aligned. And it turns out that if you do the calculation, you'll get the kappa squared will be equal to 2/3. So commonly you put in 2/3. What if you want to do a little bit better? In your measurements with Marco in the lifetime, did you guys measure what's called the polarization? Yes? Oh, you did? Okay. Good. So, so you did the anisotropy. Oh, you guys are experts in this. So why don't you tell me about how you figure out what kappa squared is, or at least put some bounds on it. So you guys, did Marco talk with you about how you use the anisotropy? Oh, yeah, let's go and look in your book there. No, that's... Okay, well, why don't you talk about it for a little bit and then get back to me, even if he didn't tell you anything. Maybe you can use your brain a little bit and figure out what the anisotropy is, or polarization. In fact, what is the anisotropy versus the polarization? And then once you know about that, or you don't, or you can't figure that out, you can determine how that comes into kappa squared. Okay, go ahead.
The board wasn't on the first half of the lab, and not the second half where we talked about it.
Okay, well,
We're gonna look up what that's really loud.
I could see it being no. So like you think about two vectors without parallel there, or perpendicular, you kind of sound like that's the like so like if you zero your anti-tail or one. But let me ask you about how you how you post your
anisotropy is the opposite of isotropy. Yeah, have the answer on your cell phone?
Maybe.
Okay.
The other, the.
So like which way you're pointing. So like and tells it to read on her center.
Are you, what, why don't you, and Michael, right? Yeah.
Which is a measure of how well.
And then I think it was something like after.
Okay, so what, oh, good. So what do we have ideas of? Let's see. So you take, why do you want to take the polarization, or how is that going to relate to kappa squared? Or the anisotropy, and what's that? Go ahead.
So can I first ask you what, how to like calculate the kappa square is like two vectors you add it together and take the modulus like this?
Ah, okay. Yeah. Hold on. Okay. Okay, in terms of knowing what kappa squared is, what you do is you take the donor, which has a dipole moment, so it has, see this little arrow, so it has some theta and phi. And you have an acceptor, which also has a transition dipole, so it has another theta prime and phi prime, yeah? And you first and say that, let's say along the, whatever, what in this case the y-axis is the plane of polarization of your incoming light. So basically you take this and you dot it into the y-axis, and so that if it's aligned, that's really good. If it's not aligned, it won't give you hardly any fluorescence. And then you're interested in taking the dot product between this D and the A to tell you how efficient it is. And yeah, and that's essentially what kappa squared is. Is that okay?
Then what is the maximum for?
What is, why is it always positive if it's not
Oh, it's because either you have some energy that's transferred, or you have none. In this case, you can't get negative energy that's transferred.
But then is it the absolute value of it, or is it the square of the dot product, or?
Actually, it is the, yeah, each case it is the square of them. So it's like the incident vector that is coming along with the incident light, and the donor, you take this dotted with this, and you take the square of it. That's right. Okay? So that's 0 to 4. Okay? But how good is this approximation or model, because this assumes that things are static, that the donor is sitting at a particular position. In fact, it may be wobbling around. So how are you going to tell if it's wobbling around during its lifetime? And that is where the polarization or anisotropy comes in. So let's talk about polarization. It's just a little bit easier to think about. So what is the polarization? Polarization. At least half of you did this. How many of you have done polarization in okay, well, that's about half. Okay, so half you did it, and half of you didn't. So, okay, you happen to be in the half that is coming up empty. It's okay. You'll do it, I guess, this week or something. Tomorrow, okay. So, who can tell me what polarization is? Mm-hmm. When you're measuring the polarization of the emitted light of the donor, what?
Or isn't like a claim as to what direction the light is emitted in?
Yeah. That's right. So what is it?
Just the plane in which the waves are not propagated.
So how do you measure the polarization?
Cosine squared of polarizer.
Good.
Intensity or something like that.
Good. So you come in with light like this, and you know, and the dipole is at some orientation, and then it goes through a polarizer that only allows this. For example, this is the parallel, and then this is your detector. So, I don't know, well, let's call it Y. So it's the electric field here along the Y direction times, you know, I don't know, cosine theta times, then in this case times, like, I don't know, of sine of theta times, again, the z component, something like that. This could be somewhat off. This is the probability that it's going to absorb the light, and this is the probability that it'll emit the light and make it through the polarizer in the parallel direction to reach your detector. And then, you know, some sort of, okay? So I have a feeling that, you know, like, you're very concerned with exactly which cosine theta or phi or, you know, the square root. I don't want you to be worried about that. What you should do is you should look at this and get a sense of, you know, what this term is and what this term is, and don't exactly be so worried about, you know, what the exact forms are, because this has to do with a general way of thinking, which in some ways is the most important thing I can give to you. Like last time, we talked about various unconstrained parameters, and you had to think about it. And that is actually what really counts. And here, again, you're thinking about, in this case, the polarization and how it's going to relate to kappa squared. And what the exact form of the integral is, you know, doesn't matter. So some form of the integral where you have parallel light, or you're looking for this parallel light, you'll get some form of that. And then you know, that, or it really should be into the board. And this is, you have now some polarization, a Polaroid that is only letting through that light that's going like this. And to the extent that it's, you know, you have a donor which is all just aligned along this vertical axis where it's coming in, basically, and then emits, it's going to do a really good job of getting through this one, and this one, it's not going to make it at all. And now let's look at if the thing is rotating during its lifetime. Well, let's say this is really rotating really fast compared to its excited state lifetime. What will actually it look like in terms of the detector? The amount here and the amount coming in here. Will one be greater than the other? Or will they be the same, or 0, or whatever? What do you think, Lydia? 50-50, meaning half and half? Yeah, yeah, exactly. That it'll be half and half, and that will be equal. So if you define your polarization as I parallel minus I perpendicular. Okay, these are in intensity. Now, so what if you turn up the light by a factor of 2? Do you want the polarization to change? No. So how are you going to normalize that out? Yeah. Divided by the total. This is the...
Should that be perpendicular?
Oh, yes. That's the polarization. So you do that for the donor. You do it for the acceptor, because remember, both can possibly move. And then from those values, you can get a good sense, a quantitative sense, of how much the donor is moving and how much the acceptor is moving. And therefore, you should be able to write an equation which can relate kappa squared to this polarization. And that's the idea. That's why you took the polarization of the donor and why you, I don't know what you actually did, the polarization, why you take it of the acceptor, is to get a sense of, to narrow down kappa squared. And in fact, so in this case, this is completely unpolarized and this is completely polarized. And, oh, no, I'm sorry. This is 0 where it's the donor is like this, the acceptor is like this. But in fact, if you have them randomly rotating, you'll get kappa squared as 2/3. So what you do is, based on these polarization measurements, you'll get kappa squared, in fact, is less than some number and is greater than another number, where this is greater than 0 and this is less than 4. Okay, and now let me just give you an additional factoid. It's basically has to do with what people prefer. It's nothing fundamental. The anisotropy is this plus 2 times I perpendicular. It's another way to normalize out the polarization or the anisotropy. There is some reasons for it, but it's not really fundamental.
So I think I'm confused.
Okay.
So when kappa is 0, the donor is like this and the acceptor is like this, and they're not moving?
And they're not moving.
Oh.
Not moving.
So it's not moving. So when it's 4, they're both in the same plane and also not moving.
That's right. Right. Now, let me actually tell you about one other parameter that is actually relevant. It turns out, right, I said a donor like this and the acceptor is like this, from here or there. There's another parameter that it could be like this or like this. And it turns out that will also affect things. So there's an additional parameter that not only has to do with the thetas involved in the donor acceptor, but also in the phi. And
it's because they can cancel it or interfere or what?
No, actually, well, you can imagine that it's the donors, let's say, like this, and the acceptor is like this, or like this, but also, let's say, it's like this. The donor is like that. And so in that case, it couldn't transfer. I think that's true. Right? Because, right.
So there's another parameter.
Another angle that you have to take into account, not only theta, but actually the phi parameter. Okay? Okay. So that's why we measure the polarization or the anisotropy, to nail down what that kappa squared. In truth, often we assume that they're both going like crazy, and if they're going like crazy, kappa squared is 2/3, because you can't always measure it. In your case, you can, but if things are in a microscope, it can be difficult. Yeah?
Well, give me like an extra magnetic field, since they're dipoles, to get them all in a orientation.
That's a very interesting point. In this case, a magnetic field would not have any, pretty sure would not have any influence on them, because this is it is an electric dipole moment. It's not a magnetic dipole moment. So you can say, oh, okay, well, your idea was really good, but instead of making a magnetic field, you should make it an electric field. Okay, and it turns out you can do that, but the size of the electric field would be enormous, because these molecules, they're a few nanometers in size, and it would blow the whole molecule apart. Okay, so the question is, we know that the energy transfer is going as 1/r⁶, and we know that it's somehow depending on the polarization. Can you actually measure this? Well, first, they actually measured it, for example, on pieces of DNA that you get longer, and you sort of somewhat plot out the 1/r⁶. Much more difficult has been the polarization. But actually, they managed to do it, although this is really quite recently. The original FRET technique was from 1967, and it was only like, I don't know, last 10 years that actually somebody took a piece of DNA, they stuck a dye on the end that did not wobble hardly at all, and took another acceptor, took it barely wobbled, and then you can see that you have the donor, the acceptor, and the donor, and now if you separate it by, let's say, 10 base pairs, the donor is here and the acceptor is here, and then you actually make another one that's 11 or 12 or 13. And so then the donor and the acceptor will be here. So you should see, instead of like instead of 1/1 plus r/r0 to the 6th, you should see a little bit better, because r0 is actually varying. And obviously, they got this to work, otherwise I wouldn't be telling you this. And I don't know if you can see, but you can see it's clearly being modulated by a function of the distance. And so, and in fact, it fits, very well to the formula that you do. Okay. Yeah.
Is the fact that it's not continuously declining like something to do with maybe interference effects?
What? you're saying it's going down, and then it's actually going up.
Yeah. Is
What?
that possibly
What?
due to interference effects? From quantum effects?
No?
DNA is a spiral.
Yeah. Yeah. Oh, yeah. I'm sorry. Perhaps you're not familiar with the. So, for example, you have a donor and, I don't know, you have an acceptor here, and let's say, you have a donor that's here. And in this case, when it's like that, there's a lot of energy transfer, and although then you cut it down and the donor looks like this, and it looks like that, and there kappa squared is 0. And so you'll get a lot more energy transfer here than you'll get here, even though this guy is closer together. And that's exactly how you get the modulation. Okay? Okay, so I think, okay, 3 more minutes. Because I have to tell you about this because it's really, really great. Because polarization studies are not only useful for nailing down what kappa squared is, it's also really useful to detect binding events. And for any of you, for example, who are interested in industry or the real life effects of this, you should be interested in this. And that, let's say, what happened to, I guess I leave it here instead of someone stealing it from me. Okay. Who knows what Pac-Man is? No, you don't know. So, I do know. No. Good. Well, when I was, oh God, I don't want to say how long ago, but I was, I got to tell you this story. Okay, this will take an extra minute. I was a senior undergraduate. I went to Michigan, and I was totally into Pac-Man. I mean, I was like addicted. How would you say that I was addicted? On the way, I had a final in my quantum mechanics class. I stopped off to play a game of Pac-Man. And I had become, at this point, put enough quarters in that I had become pretty good. And so it was like going and going and going until I was going to be late. So I had the choice. Either I could be late to my quantum mechanics class, or I could do suboptimally on my Pac-Man. Which do you think I chose? Down the tubes, man. So anyways, this is a little Pac-Man, but it happens to be in your body. And its job is to take a little ligand. So this Pac-Man happens to be a protein, and its job is to bind this ligand. And in some cases, for example, if you have cancer or something like that, this is very legitimate. True, this binding is too good or not good enough. So how do you go and detect whether this ligand will be bound to this protein? Well, what you do is you take a small little fluorescent molecule over here, and let's say when that fluorescent molecule is on the ligand, it's small. So what is its polarization? Will it be high or low?
Low.
John, that's right. It'll be really low. So now you let the thing bind. And let's say it all binds. In which case, this protein Pac-Man is really big. So the rate at which it tumbles is very slow. So now, when this ligand is actually in here, it too will be tumbling very slowly. And so this fluorescent molecule, it too will be tumbling very slowly. Remember, what counts is on its lifetime. So in that case, what will its polarization look like? Okay, so how do you make an assay out of this? And they've done this, and it's made an enormous difference. For example, if you want to find a drug against breast cancer, how do you do it?
You label different types of molecules and look at which one has high polarization.
That's right. In fact, and what you do is you take a woman who has breast cancer and another normal woman. And the difference is with cancer, she has something that binds to this ligand with a tremendous affinity. And with normal, she doesn't have one that doesn't bind with affinity. So first thing you do is you can test them to see, okay, you have a little Pac-Man which is binding like crazy, therefore you have this type of cancer. And in fact, there is nowadays like 3 different types of cancer. They're her positive, her negative, and her is the protein. And there's a couple of other kinds. So first you see, okay, what type of cancer do you have? And then how do you want to make a lot of money. Plus, of course, you want to actually, save the woman's life. So how do you find drugs for it that can interfere with it? So you have, for example, you have ones that you have estrogen, which is common ligament, and then you have EGFR, which stands for epidermal growth factor receptor. So what you do is you throw in a bunch of estrogen such that they're all bound. But the estrogen, that's it, doesn't have any fluorophore on it. Then you throw in a compound A, or compound B, or compound C, all of which have a fluorophore bound to it. If it can't compete with estrogen, it stays out here, and it has low polarization. But if it can compete with the estrogen moves out, the other ligand moves in, and it has a high polarization. So what you can do is you not only do compound A, compound B, compound C, but multiply that by a few million compounds. Okay, and that's what they do. They're actually doing this sort of right now. And eventually, they find a drug that actually works that outcompetes estrogen or something like that. And then, after they go through the killing some mouse and that sort of thing, they actually go and feed it to women, and then either it works or it doesn't. And that's how legitimately how they go about making these new drugs. Often it's one test is fluorescence polarization. Yeah?
How would you know if the drugs were binding to EGFR instead of some other protein?
Yes, that you have to make sure that, for example, you take one with a cell that has, let's say, EGFR expressed, and another one that doesn't have EGFR.
Oh, okay.
That absolutely you have to do that sort of test. And in general, this sort of molecular biology has been done. Although, yes, it's absolutely critical that you know, in this case, the ligand, like being the estrogen, and the protein being the EGFR.
And how would you know whether or not the binding too much or too little is a cause of the disease rather than symptom?
Well, that's another big question, and you often don't know, in fact.
You would have to find something that stops it, or you would have to find something that causes it to bind at a normal level, and only then would you figure out whether or not it was the cause of this.
Yeah, that's right. In fact, you don't know whether the thing is binding too heavily or not enough, because that can be a problem also. In this case, in the estrogen case, in the EGFR, they actually know that it's binding too heavily, and then actually once they've designed a drug and they give it to people, they actually have to see does it do anything? That is, you assume even that it will interfere with estrogen binding, but you're right. Is that a driving cause of it, or is that just some sort of, bypass? And you don't know until you do the studies, or you make some studies on some mice, and you can. That's what you do. So you give cancer to some mice.